Hello everyone, welcome to my channel. In this video, I have a very intriguing integral that I would like us to look at. So it is the integral of e to the power x times the square root of 1 plus e to the power 2x dx. Now, how do we approach this? What kind of technique of integration are we supposed to use? Well, normally when you have the square root sign, you would want to start from under the square root sign and see if you can manipulate that so you have, after differentiating, the expression outside dx. But in this case, it is not possible. So how do we approach this? Well, watch how I'm going to transform this integral. So we have the integral of e to the power x times square root of 1 plus e to the power 2x dx. Watch the transformation of this integral. This is going to be equal to the integral of the square root of, watch this, 1 plus e to the power x, and I'm going to have to say squared, and then outside I have e to the power x dx. Using laws of exponents, you'll agree with me that e to the power x squared is just e to the power 2x. But at this stage now I have to say let t be equal to e to the power x. Differentiating both sides, you'll agree with me that the t is equal to e to the power x dx. Now, this expression is that expression, as you can see. That place there now must be taken up by t. So the integral then is transformed as follows. It will be the integral of the square root of 1 plus, watch this, t squared, and outside here I just have dt. Now, at this stage, you will agree with me that trig substitution here should be very useful. You say, why do you say we must use trig substitution? Well, you would recall this one here. Sine squared theta plus cos squared theta is equal to 1. A very basic trig identity that. And therefore, if I divide throughout by cos squared theta, this trig identity changes to sine squared of theta over cos squared of theta plus cos squared of theta divided by cos squared of theta. So sine squared of theta over cos squared of theta plus, remember we're dividing every term by cos squared of theta, and we are going to have 1 over cos squared of theta. Obviously, the assumption here is that cos squared of theta is not equal to 0. That's the assumption. Now this, you'll agree with me, this is tan squared of theta, and then plus 1 equals, you'll agree with me that this is sec squared of theta. So when I see this, I see this. Now, if you look at the expression under the square root sign now, 1 plus t squared truly resembles this part here. If you write it as 1 plus tan squared of theta, this one here resembles that expression. So I'm going to now let's say let tan of theta be equal to t. Remember, when we use trig expressions or trig substitution, you must immediately draw your triangle because you're going to need it. So we have a triangle here, right angle triangle, and our theta is defined as this angle here. And remember, tangent is the opposite side over the adjacent side. So it has to be written as t over 1, which means my opposite side is this one, the adjacent side is that one. By Pythagoras theorem, this one should be the square root of 1 plus t squared. You'll agree with me that that's the case. Now, in order to obtain the expression for dt, we'll have to differentiate both sides, this expression here, or this equation here. So derivative of tangent is secant, as you'll agree with me. So now I'm going to have sec, derivative of tangent is secant squared. Sec squared theta d theta. On the right hand side, we have dt. So now in place of dt, I'm going to have sec squared theta d theta there. And here I will have tan squared as follows, taking us to page 2. Hopefully you can easily follow what I'm trying to do. So now we are basically saying we have the integral, check this, the square root of 1 plus tan squared theta, and outside what am I supposed to have? Instead of dt, I'm going to have sec squared theta d theta. So sec squared theta d theta. Now we have transformed it into a trig or an integral involving trig expressions. Now notice something here. This is the integral of the square root of what is 1 plus tan squared. Well, from here you can see that 1 plus tan squared is actually sec squared. So now I'm going to replace 1 plus tan squared by sec squared in this intervals, in this integral. So we now have sec squared theta times sec squared theta d theta. Now this cancels that. What are we saying? So we have the integral of sec of theta sec squared of theta d theta. This changes to the integral of sec cubed theta d theta. Now this one here is quite an integral as well. So how do we approach this? Well, I am going to perform, remember these are techniques of integration. If you like, advanced techniques of integration, calculus 2. So how am I going to evaluate this? Well, I'm going to have to break this one down as follows. Watch this. I'm coming back to there, but this is necessary because this one will come up in the process. So we needed this one. But let's go back to that form. So going back to that form, we're going to say this is the same as sec of theta and then sec squared of theta d theta. And at this stage, I'm going to use what we call integration by parts. I'm going to use integration by parts. So what is the approach? Well, the approach is now we're going to select u be equal to sec of theta. And at the same time, if you remember the integration by parts, we have to say dv. And dv must be equal to this part here. So it would be sec squared theta d theta. Differentiating both sides, we know derivative of a secant is actually sec theta here in this case, tan theta, and then we have to say the theta. On the other side, we integrate both sides. V is going to be what? The integral of sec squared, where it's tan. So we have tan theta. Going to page 3 and employing integration by parts formula, basically it says the integral of u dv is equal to uv minus the integral of v du. Now notice something. This part here is our sec cubed theta d theta. You say, why are you going back to there? You understand why I'm doing this. But remember, this part here is that part there. We just had to break this one down back into that format so that we can actually use let u be equal to this and then dv equals that and then carry on with our integration. But now we are saying, what is u? Well, u is sec theta. You can see it here. So I have sec theta. What is v? Well, v is tan theta. So now I have tan theta here minus the integral of what is v? Well, v is tan theta. So now I have tan theta there and times, let me put brackets here. What is du? Well, du is sec theta tan theta d theta. So now we're changing that to sec theta tan theta, and then we have d theta. Now let me move back because of space. So I'm going to say that is exactly equal to sec theta tan theta minus the integral of, if you multiply these out, you're going to agree with me that it's actually tan squared theta sec theta d theta. Fantastic. Now let me take you back to the trig identity that I have explained here. Look at this one. 1 plus tan squared theta equals sec squared theta. So therefore, if I want to solve for tan squared theta, you agree with me that this will be tan squared theta will be equal to sec squared theta minus 1. Obviously, it follows from there that this is the case. Now, what are we saying? We're saying where I see this, I must place that expression here. So this is going to be equal to sec of theta tan theta minus the integral of, let me use brackets here now. And in that place there, I'm going to put sec squared theta minus 1. And we have outside sec theta, and then we have what? D theta. Now I'm going to use brackets here because I don't want that minus sign to mess up what I have inside there. Now I'm going to distribute the integral and sec theta d theta and watch what happens. So this is going to be sec of theta tan of theta minus, and I'm going to have that bracket there, So it will be now the integral of sec cubed theta d theta minus, remember this now has to multiply by that, it will be the integral of sec of theta d theta. Now removing these brackets here, you'll agree with me that this is equal to sec of theta tan of theta minus the integral of sec cubed theta d theta plus the integral of sec theta d theta. Where are we coming from? Don't forget, we're coming from the integral of sec cubed theta d theta there. So now I'm saying, therefore, we are saying that the integral of sec cubed theta d theta is equal to this part, sec of theta tan of theta minus the integral of sec cubed theta d theta plus the integral of sec theta d theta. Now notice this part here is exactly that part. So I'm going to take this integral to the left hand side, or add this on both sides. We're going to get twice the integral of sec cubed theta d theta, and this is equal to sec of theta tan of theta. The integral of sec theta d theta is actually natural log of sec of theta plus tan of theta, and that would be absolute value. So the integral of this part here equals that part there. And the easiest way to show this is by differentiating this. You are supposed to find sec theta. If we have time, we're going to try and go do that. So now we have a 2 outside. I have to divide throughout by 2, taking us to page 4. So basically now I'm saying we're almost done. I'm saying now that that is implies that the integral of sec cubed theta d theta will be equal to dividing by 2 throughout. This is going to be half of sec of theta tan of theta plus half of natural log of sec of theta plus tan of theta, and then I have to say plus c because we're dealing with an indefinite integral here. But now let's move back, because this is not our original variable theta. We have to go back to our original variable, which is x. But remember, we had to have t in between. So what is the relationship between theta and t? There it is. T is tan theta equals t. So therefore, where there is sec theta, you can actually see it from here, that secant is the hypotenuse over the adjacent side. So it will be square root of 1 plus t squared, and that will be in that place. Tan is 1 over t over 1, which is t. So this therefore changes to, if you agree with me, by using this triangle here, let me put it up there so you are able to see. This is on page 4. Therefore, our solution is transformed to half. What is sec theta? Well, sec theta is hypotenuse, it's reciprocal of cosine, obviously. So it will be that over that. So it will be square root of 1 plus t squared, right? And then what is tan theta? Well, it's actually from here you can see tan theta equals t. Tan theta equals t. I hope you can see it there. Yes. So that will be t. And then I have plus half natural log of. Now, what is sec theta? Well, sec theta, like we said, is square root and a positive square root. Let me maintain the absolute value signs for now. I will see whether we can keep it there or not. So this will be 1 plus t squared. And then we have to say plus. What is tan theta? Well, tan theta is t, as you can see it here, t. And I'm going to say this plus c. Now, so let me rewrite this part here. So this is going to be equal to, if I move back a little bit, it's going to be equal to half of t times square root of 1 plus t squared, and then plus half of natural log of, let me maintain that, square root of, because of t, we'll see whether we have to keep the absolute value signs or not, 1 plus t squared, because this part will never be negative, but that t here could be negative depending on the value of t. So we have t and then plus c. But let's go back to our original variable x. What is the relationship between t and x? Here we go. T is equal to e to the power x. Now we see that this can never be negative. So now I'm changing this. So this will be, so we can just maybe conclude and say, therefore the integral of e to the power x times square root of 1 plus e to the power 2x dx, this one changes to, we are there now, half of e to the power x. Remember, t is e to the power x there. T is e to the power, here, you can see it clearly there. T is e to the power x. So where there is t, I put e to the power x. So that will be terms where, remember, this is our solution there. I'm removing t and I'm replacing it with e to the power x. That will be square root of 1 plus t squared. It will be e to the power x squared, which is just e to the power 2x, the original expression. And then I have to say plus half of the natural log of, notice now I have to use round brackets because this part will never be negative, square root of 1 plus e to the power 2x, we're squaring t, remember, plus t is e to the power x and plus c. So that would be the final solution to our integral in this video. Advanced cases of u-substitution and Trig expression combined, like I promised. So this is one integral where we are employing three techniques of integration. One is the u-substitution coming here in the form of t, and then we have Trig substitution there, and then we have integration by parts over here, where we had to split that into, where is my page 2? Here is page 2, where we had to split sec cubed theta into sec theta, and then sec squared theta d theta, and then used integration by parts from page 2. Remember the uv substitution. Here is our page 3. We had to use integration by parts, managed to evaluate the integral, coming up with our final solution, that, and then we had to go back to the t as a variable, the intermediate variable, if you like. We used t, and then we had to move back to our original variable, which is x, in our final step there. So this is how you evaluate this integral here, looking very humble and simple, but you know processes involved quite a lot. All right, we learn mathematics by actually doing it. So remember that practice makes perfect, as they say. Right, so if you're new to this channel, support us by subscribing. Let me know if you have other techniques of evaluating this integral. I'll be interested to look at those techniques. All right, I'll see you next time.